Before I go back to what happened last time, I need to make an announcement. It's a very sad announcement. Last Wednesday, I gave you back your homework, and then I gave you back a bit more of the homework during the tutorial. And then I left the homework spread on the table, and I left the classroom, and then I realized I left the homework on the table, and I came back, and it was locked. And then I came next morning to collect your homework and preserve it, and it was gone. And I looked for it, and I was told that it was put in the recycling bin. So I went to the recycling bin, and I looked for your homework, and it wasn't there. Right. So if you have not collected your homework, then your homework is now being recycled. I'm sorry about that. So if you can think of a way I can make it up to you, then please let me know. If you want to resubmit it, I'll be very happy to regrade it. If you just want to come to my office and tell me what you've done, and I'll give you, without having to write it again and ask for my opinion, then I'll be happy to do that. And if I manage, if I have the chance to go to the recycling place and find your homework, I'll do that. I'm not sure you're going to want it back, but that's another thing. Okay, so now that I've come clean, let's see what other weird things I'm going to do. Okay, so I want to go back to what happened last time. And last time I started by asking you a trick question. So what was the trick question? We were looking at a European call option on an underlying asset price, an underlying asset whose price was £10, and then we looked at what would happen at expiration. So this option expires in 1 year, and then we had a view on what's going to happen at expiration, and then we said, let's draw a picture of the world. So we start with an underlying asset price of 10, and then the underlying asset price can go up to 11 or down to 9. Now, if we're talking about a European call option expiring at this time with a strike price of 10, that this means that in this state of the world we would get a payoff of 1, and here we would get a payoff of 0. Where this is coming from is from the definition of a call option, which you now should know very well. If someone wakes you up in the middle of the night and asks you what is a European call option, you would say it's a contract that gives you the right to buy something at a certain price. So you can, if you find yourself at this state of the world, you can buy something for 10 and sell it for 11, and then you can make a profit of £1. Here you have the right to buy it for 10 and sell it for 9, because that's the market price in this state of the world. So you're not going to do that, and then your option is worthless. And then there were two people, Mrs. X, who said, you will find yourself in this state of the world in a year with probability 1/2, so she will get a payoff of 1 with probability 1/2. And then there was this other person who said, no, you're going to find yourself here with probability 1/3. So the expected payoffs of these two people were 1/2 and 1/3. And I asked you who is going to be willing to pay more for this option. And then I spent the rest of the lecture convincing you that they're both going to be paying the same for this option. So let me take you quickly through the argument I gave you. In fact, not only did I convince you that they both pay the same, but I told you how much they pay. So what was the argument here? So let me repeat myself. This is the picture I've just drawn on the board. So make sure that you understand that we're dealing with a very simplified story of the world in which we are at some point in some state of the world, and then we wait for a year and we can find ourselves in one of two states. So we're dealing with this very simple model of the world. And then we said, let's construct an interesting portfolio. Let's construct a portfolio which has some unknown number delta of shares of this stock. So we have delta units of this thing which cost now 10 and will cost either 11 or 9 in a year, and minus 1 call options. So what does it mean, minus 1 call options? We issue a call option. And now if we find ourselves in this state of the world, we're going to lose £1 because someone is going to buy this stuff from us for 10, but we're going to have to go to the market and buy it for 11. So we're going to make a loss of 1, and in this state of the world, nothing is going to happen. Okay, so we have delta shares and minus 1 option, and then we say, let's choose delta cleverly. Let's choose it so that no matter where we find ourselves in a year, either this state of the world or this state of the world, the portfolio is worth the same. So we say, how much is the portfolio worth in this state of the world? And we said, okay, we have delta shares in this state of the world. Each share sells for 11. So this is the value of the shares in the portfolio. And we have minus 1 option, so in this state of the world, we lose £1 because of the option. Here, in this state of the world, we have delta shares. Each one trades for £9, and the option is not exercised, so we don't lose any money. So these are the prices of this portfolio just constructed in 2 states of the world. And I'm going to choose delta cleverly enough so that these 2 numbers are the same. So I set this to be that, and I solve for delta. And when I do that, I get some value of delta, in this case, half. So we're talking about, let's assume that you can buy and sell half a shares. So you have a portfolio which has half a share in it and minus 1 call options. And then we said, okay, so in this portfolio, no matter what happens in the future, it's always going to be worth the same. So for example, let's take this expression for the value of the portfolio in 1 year to calculate how much it's going to be worth. So we have 1/2 times 9, which is £4.5. So no matter what, this portfolio is going to be worth £4.5 in a year. Okay, so what is so good about that? So we have an asset now, this portfolio, whose price is known for sure to be £4.5 in a year. And we had a homework problem that said, if that's the case, if you have an asset whose price is known in advance, then the price now of that asset, it's the present value of its price in the future. Right? So how do we compute present values? We take the value in the future, the known value in the future, £4.5, and we multiply this by e to the minus 1 year interest rate times 1 year. So here it is. Here's how much the portfolio must be worth now at time 0. It's a present value. This is the number used to convert the value in the future to present value. It's a present value of the certain value of this portfolio in 1 year, which is 9/2. On the other hand, we look at this portfolio and we say, how much would we have to spend now to buy this portfolio? So we say, okay, there's half a share in it. 1 share trades for 10, half a share trades now for 5. We have a call option whose price we're trying to find. Let's give a name to the price of that option. Let's call it C. So we have minus 1 call option. So what's the contribution of this minus 1 call option to the price of the portfolio? How much do you have to pay to buy minus 1 call options? You have to pay minus C. So you're paying a negative amount of money, which means that someone is paying you money when you issue this option. Okay? Then we said, okay, so the value of the portfolio can be written in 2 ways. This is way number 1, this is way number 2, and now we can use this equation here to find the value of C. So we solve for C, and we get this expression here, which you can now take out your calculators and get the numerical answer of 72 pence or so. So we look at this calculation and we say, who was willing to pay more for this, Mrs. X or Mr. Y? Well, the answer is nowhere in this calculation did we use the beliefs of Mrs. X and Mr. Y about the future. We didn't take into account how probable they think that the share price is going to be 11 in a year. So they're both willing to pay the same, and in fact we know exactly how much they're willing to pay. It's that number we just calculated. Okay? So this is what happened a week ago, not that long ago. So I'm hoping that you still remember this story. So is this okay? Do you remember what happened here? Do you have any questions about this? Okay, so what we're going to do next is we're going to take this simple example and we're going to generalize this. And we're going to end up with a way of finding prices of derivatives in very simple worlds. So the first kind of world we're going to consider is a world like this, in which we are at some state of the world. Then after some period of time, after we get to expiration, we're going to find ourselves in two possible states of the world. And then we're going to say, okay, let's take that as a building block for more complicated worlds. So we can take now worlds in which you start with some state of the world, and then after one step in time, we can find ourselves in two other states of the world, and then from each one of these states of the world, we can find ourselves in two other states of the world, and now we can construct more complicated worlds. That's one of them, for example. It's not a very plausible one, but that's one example of the kind of world which we're going to be able to deal with at the end of this lecture. And then you can ask me, but why should I worry about simple worlds like that? We don't live in this simple world. And then I'm going to tell you why we should be worrying about that when we finish these constructions. Okay, so let's generalize what I've just shown you. So now we're going to look at some financial asset that provides no income, which is going to be the underlying asset for some derivative. Remember, a derivative is some financial asset whose value depends on the value of something else. So a derivative has a value which depends on the value of some underlying asset. So we're going to consider a financial asset, which is going to be some underlying asset for some derivative. We're going to assume that that underlying asset provides no income. Then we're going to be looking at some derivative with that asset as an underlying asset. And let's assume that this derivative produces a single payoff t years in the future. Okay, so that's an example of that. We are looking here, this time step was 1 year. So in this case, 1 year is t. And now let's give names to various things. So let's start with an asset price. So I'm going to modify that picture over there. So we're going to start with some asset price. So instead of a 10 here, I'm going to start with a general asset price. And then the asset price after t years is going to go either up or down. And let's assume that it can go up by a factor of u. Let me just make some order here. So suppose that the underlying asset price can go up by a factor of u. So if it goes up by a factor of u, s becomes s times u, and u is some number which is greater than 1. Or the other state of the world we can find ourselves after t years is that the asset price, the underlying asset price, goes down by a factor of d, and here d is some number between 0 and 1. Okay. And then we have some derivative that gives you a payoff at expiration. And we're going to give names to the payoffs. So it's going to be some payoff which depends on the underlying asset price at expiration. And we're going to call these payoffs p's of u. So it's not p times u, it's p's of u. P, the payoff in the up state of the world, and p's of d, which is the payoff in the d state of the world, in the down state of the world. And we're going to ask ourselves, how do we find the price of such a derivative that gives you these payoffs? And then we're going to have to use another number here. So let's take r to be the t-year interest rate. Let's write it. R is y of t the value of the yield curve at time t. It's a t-year interest rate. Okay, so let me repeat this picture. This is the picture we're looking at. And we're going to find the price, the value of this derivative at time 0. And how do we do that? We're going to construct a portfolio. And what sort of portfolio are we going to construct? We're going to construct a portfolio which has some number of units of the underlying asset and -1 derivatives. And we're going to choose the number of units of the underlying asset so that no matter where you find yourself in the year, in which state you find yourself, up or down, the portfolio has the same value. Okay, so how can I do that? So I want to choose how many units delta of the underlying asset to put in the portfolio. And then I'm going to choose it so that the portfolio has the same value in the up and the down states of the world. So let's write down what is the value of the portfolio in the up state of the world. So let's see, here, let's do it in blue. I'm going to have delta shares. Each one of them is going to trade for S times U. And I'm going to have -1 derivative. This -1 derivative is going to cause me a loss of PU. So I have to subtract PU. So that's the value of the portfolio in the up state of the world. How about the down state of the world? Well, I still have delta shares, delta units of the underlying asset. Now the price is S times D. So that's the value of the underlying asset component of the portfolio I'm constructing. And here the derivative of which I have -1 of gives a payoff of piece of t, which is then my loss. I lose piece of t. And now how am I going to choose my portfolio? I'm going to choose my portfolio by choosing a delta that makes these two numbers the same. Okay, there it is. I want a delta that makes these two numbers the same. I can bring all the deltas to one side, and I can then isolate delta, and I'm getting delta is equal to that, piece of u minus piece of t divided by S times u minus t. Okay, so with this choice of delta, I can ask myself what's going to be the value of this portfolio in t years, where I know that it's going to have the same value in this state of the world or that state of the world. So what is that value? So I can take either the expression on the left or the expression on the right and substitute this value of delta into them. So let's take, for example, the expression on the left. So I take this value of delta and I substitute here, and I'm going to get this is the value of the portfolio in any state of the world. And now I'm going to simplify this a bit. There's going to be an S here, an S here cancelling an S here, and I end up with this expression. So no matter what, if there is a huge disaster and the share price goes down, or if there is a wonderful bonanza and the price goes up, no matter what, your portfolio is going to be worth that expression in t years. And again, I appeal to the homework question that you may have looked at, which says if you know that you have an asset which is going to be worth this number much in t years, then the price now must be the present value of this amount paid in t years. In other words, it must be worth e to the minus t year interest rate times t times the nominal value in t years. Okay, is this making sense? Do we have any questions about this? Okay, so if this is making sense, then what else can we do? So now I say, okay, let's look at this portfolio. It must be worth that. But I can also look at this portfolio, and I can think of the price of this portfolio by doing something different. I can ask myself, how much money do I have to spend now to buy this portfolio? So let's buy this portfolio. What do I have to buy? I have to buy delta shares. Now the shares are worth S. That's what we call the spot price of the underlying asset. So I'm going to have to spend, this is how much I spend to buy 1, this is how much I'm going to spend to buy delta, and I'm going to have to buy -1 derivative. If we give a name to the price of the derivative, if we call it x, then buying -1 derivatives is the same thing as issuing a derivative. When I issue a derivative, I get x pounds, which means you can think of this as costing you -x pounds. So this is the price of a portfolio times year. We know what delta is. We just computed it. We can use its value here. So let's do that. So here's what we just said the portfolio must be worth. That's the present value of this certain value of the portfolio in t years. On the other hand, it must be worth delta s minus x, this expression over here. Now let's remember what delta is. Let's substitute the value we found for delta in here. We're left with that. Again, some things are going to cancel. S and S cancel. We're left with this. We can solve for x. We can solve for the value of this derivative at time 0. And we're getting this. And you can rearrange things a bit. And you can end up pulling this expression outside. And we're left with that. And now I'm going to do some magic. I'm going to define a new number. The new number is going to be called q. And it's that q over here. So if I use this value of q to try to simplify this expression we just produced, and by doing not terribly interesting things, arithmetical things, you can rewrite this expression. This expression is this one using this expression for q. And now you can look at this and you can ask yourself, why am I bothering with this q? What is this q doing for me? Suppose that I told you that q is a probability. And suppose that I told you that q, I'm not telling you this, but suppose that I did. Suppose that I was telling you that q was the probability of finding yourself here. I'm going to put this question mark so that you realize, or you should realize that I'm not claiming that this is true. But I'm saying assume that you knew that this is the case. You find yourself here with probability q and here with probability then 1 minus q. I really want you not to get confused. This is false. And this is false too. So I'm just fantasizing and saying, suppose that this was the case. And now we look at that expression over here. So in this fantastic world, this science fiction world, what is the value of the derivative? What is x? How can you think of x? What's this expression here? The probability of being in the up state of the world times the payoff you get at state up, plus the probability of finding yourself in this down state of the world times the payoff you get in the down state of the world. We have a name for that. If I give you this many pounds with this probability and this many pounds with this probability, then this expression is what? Why 0? Suppose I say I give you £1 million with probability half and £2 million with probability a half, and then I say, what is the expected value of your payoff, right? So this expression here is the expected value of the payoff, assuming that q is the probability of finding yourself here. And now let's continue a bit more. So what is this whole expression? This would be the present value of the expected payoff of the derivative. But this is all nonsense because with q, we don't know if it's a probability, and if it is a probability, probability of what? But let me convince you now it makes sense to think of Q as a probability and probability of something interesting. So let's get there in 2 steps. So first, Q can plausibly be a probability. Q is a number between 0 and 1. Why is that? Let's have a look at where this Q is coming from. So we have e to the RT minus d divided by u minus d. Suppose that it's not between 0 and 1. Suppose that it's less than 0. If it's less than 0, what is this saying? They're saying the denominator here is 0. And what is this telling us? It is telling us, suppose you compare what happens if you put your money in a safe, completely safe saving account, then after t years you multiply your deposit by this one, by this number, or you invest in this underlying asset, in which case you multiply what you started with either after a year you're going to get your deposit, your investment times d, or your investment times u. The worst case scenario is that you get your investment times d. And then when you compare what you get when you multiply your investment by this and by that, then putting your money in the bank is always worse than the worst possible thing that can happen to you if you invest your money in this underlying asset. Is this possible? So I say you have 2 ways to invest your money. You can do one thing, you can do the other thing. For the other thing, the worst case scenario, the nightmare scenario for the other thing is better than what will happen to you in the first thing. Will anyone invest in the first thing? No, right? So no one would put their money in a savings account. Everyone will invest their money in this underlying asset. The worst that can happen to them is that the investment is going to be multiplied by a factor of d, which is always better than the investment being multiplied by this factor, which is what happens if you put your money in a savings account. So this is impossible. What other things can happen here? Can this be greater than 1? Well, what does it mean for this to be greater than 1? It means that this is bigger than u, right? So you can put your money in the bank, or you can invest your money in the underlying asset, and the best thing that can happen to you if you invest your money in the underlying asset is not as good as putting your money in the bank. Would anyone invest their money in the underlying asset? No. So this is not true either. That's why this number q is a probability. It's some number between 0 and 1. So let's think of q as a probability then. But the question is then a probability of what? So let's try to figure out. Before we figure out the probability of what, let's do what we've done before I came to this slide. Let's ask ourselves, what is then the meaning of this expression we had for the price of the derivative? Now we look at this and we say, we take the expected payoff of the derivative, you multiply this by e to the minus rt, so the value of the derivative in a world in which the probability of finding yourself here is q, is the present value of the expected payoff. So I'm just repeating myself. But now let's ask ourselves, what happens, in which world do we have a probability of q of finding ourselves in the up state of the world? Let's see if we can identify that world. So let's see. Suppose that there is such a world and we ask ourselves, what is the expected value of an investment in this underlying asset? So we buy this underlying asset for S, and then with probability q, we end up with something worth S times u, and with probability 1 minus q, we end up owning something whose price is S times d. So the expected value of our investment of S pounds is this expression here. And now we remember what q was, and we can pull the q first outside here. We isolate the q here, we remember what q was, And we get this when we substitute the value we found for Q, here it is, in here. Some good things are going to happen. The U minus D is going to cancel the U minus D. And then after the cancellation, we're getting this. And after we simplify this a bit further, we end up with that. Okay. So what is this saying? This is saying you can take your S pounds and you can invest in this risky asset. Sometimes the price is going to go up, sometimes the price is going to go down. You can take your money and put it in a savings account, giving you an interest rate of R for 40 years. In both cases, you're getting the same expected payoff. Right? The expected payoff if you put S pounds in a savings account is this, and the expected payoff if you invest in this underlying asset in that world, in which this probability is Q, is the same. It's e to the RT times S. That's what we've just computed. What sort of a world is that? Do you remember the beginning of this course? I said, here's a game. I toss a fair coin. If it's heads, I double everything you have. If it's tails, you lose everything you have. And then you said, no, 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 we're not going to play this. Right? So I gave you two games, not doing anything or playing that game. Both had the same expected value. One of them was risky, the other one was not. Okay? I'm showing you two investments. They have the same expected value. One of them is risky, the other one is not. Can such a thing happen in our world? No, we don't like risk. If we're going to invest our money in something risky, we want an expected return which is higher than the risk-free return, right? But suppose that we do land, we fly to some planet, we land there and we observe this probability Q of the share price going up. So what can we say about the people living in that world without offending them? They're risk neutral. They don't care about risk. I offer them a choice to play this game with heads and tails. They say, sure. Okay? If you give them the same expected returns, they don't tell the difference between the games. The only thing they care about is expected returns. They don't care about risk. Okay? So there is a world in which the probability of the asset price going up is Q. We have a name for the people who live in that world. These are risk-neutral people, people who don't like risk. And we have a name for that world. That's a risk-neutral world. So in this risk-neutral world, in which investors are indifferent to risk, which is not our world, we can go back and say, in that strange world, the value for the derivative is the present value of the expected payoff. So if you want to know what's the price of a call option, go on a spaceship, go to that planet where people don't care about risk, observe what is the expected payoff of this derivative, find the present value of that, and that's going to be the price of this derivative in any world, not just in the risk-neutral world. And why am I showing you that? Because this way of finding prices is going to be very useful, and we're going to use it in a very different context. So this is really interesting. And now, unless you want to ask me any questions, I'm going to show you an example. But before that, I want to go back to these Qs and 1 minus Qs. So we started by saying, well, these are just numbers I compute, and then I convinced you they can be probabilities, and then I found that these are probabilities in some risk-neutral world, and I'm going to give a name then to these probabilities. These are the risk-neutral probabilities. The risk-neutral probability of the underlying asset price going up is Q, and the other one is 1 minus Q. And the method of finding the prices of derivatives by looking at the present value of the expected payoff is what we're going to call a risk-neutral valuation, which we're going to be doing later in the course as well. Okay. Do you want to ask me any questions about what I've just done? if you don't have any questions, say no, so that I know that you don't have any. Okay, so in that case, let's have a look at an example. And let's have a look at a underlying asset, some stock, some shares in some company whose current price, the spot price, is £20, and in 3 months the price is going to go up to £22 or down to £18. And let's suppose that we're looking at some European call option on this stock, which expires in 3 months. And let's say that this European call option has a strike price of 20. Let's draw a picture of that. We should do it here. So we live in a world that looks like this. We start with an underlying asset whose price is 20 now. We observe this price now. And then after a step in time of 3 months, a quarter of a year, we're going to find ourselves in the state of the world in which the underlying asset price is £22 or £18, I think, £18. And we're also told that the 3-month interest rate is 5%. So let's write this as R is 5%. And let's see if we can find the price of this call option. And let's start by asking ourselves, what is the probability in a risk-neutral world of this event? So what I called before Q, let's not call it P. So this is with probability P, but not in our world, in a risk-neutral world. So let's see if we can find what P is. You're screwing your eyes, so let me just read it for you. With probability P in a risk-neutral world. This is what I tried to write there. So let's see if we can find what is P. So let's go to this risk-neutral world, and we go to people there, and we say, okay, you have £20, you can do 2 things. You can take your £20 and put it in a safe saving account. You do this for a quarter of a year. After a quarter of a year, you're going to find that you have your £20 times e to the 5% times a quarter. Another thing you can do with your £20 is invest in this underlying asset. So let's see, what's the expected value of your investment of £20 after a quarter of a year? Well, you're either going to have £22 times P. Why P? Because this is the probability in the risk-neutral world, and we flew all the way to a risk-neutral world, plus 18 times 1 minus P. So you can invest your money in a savings account or in this underlying asset. The expected value of your investment after a quarter of a year is either this or that. Then this person says, well, people say in this world, I only care about expected returns. So if you show them 2 investments, they're going to always invest their money in the investment with the highest expected return. Which means that in such a world, all investments have the same expected return. Because if one investment has a higher expected return than the other, everyone is going to invest in that and stop investing in the others. The price of the others is going to go down, and then the returns are going to go up, and everyone is going to be buying this then, and the price is going to go up, which means that the returns of buying this investment are going to go down. And this is going to happen until things stabilize. So in the risk-neutral world, everything has the same expected return. This is by supply and demand. So, in particular, these 2 investments must have the same expected return. So we say, so this number must be equal to this number. We can find out what P is. So here, this much, this is e to the r times t, must be equal to that much. So we can solve for P. We get P is equal to that. And now we know if we were to go to this risk-neutral world, the probability of finding ourselves in the up state of the world would be P, which is equal to that number. So now we know to find the price of our call option. What is the price of our call option? It's the expected return, the expected payoff in a risk-neutral world discounted to the present. So it's the present value of the expected payoff in a risk-neutral world. Okay, so now what's the payoff of this European call option with strike price 20? Here we'd get a payoff of 2. Here we'd get a payoff of 0. So the price of this derivative is e to the minus interest rate times a quarter of a year times p times 2 plus 1 minus p times year. Here's the expected payoff of this derivative with this particular p, and the present value of this expected payoff is that number 2p times e to the minus interest rate times time. We know what p is, we can compute this, and we come up with this number. Do we understand this example? Do we have any questions about this? Okay. So now, let's take this very simple kind of world and let's see if we can construct something a bit more complicated. So now, let's assume that instead of living in a world in which one of two things happens after one step in time, let's suppose that there are two steps in time. So we're going to look at some derivative on some underlying asset. We're going to start with an underlying asset price of S. And then after some step in time, which I'm going to call delta t. So after delta t years, I'm going to find myself in the up state of the world or down state of the world. So here the underlying asset price is going to climb to S times U. And here it's going to go down to S times D. So again, U is some number greater than 1, and D is some number between 0 and 1. And then, but the world doesn't end here, there's going to be another step. So after this one step in time, there's going to be another step in time, say of the same magnitude, another delta t years elapse. And then from this state of the world, again, the underlying asset price can go up by a factor of u. So now it's going to be S times u squared. Or it can go down by a factor of d, and now it's going to be S times u times d. And the same thing from here. So we can either go up, the underlying asset price can go up by a factor of u, in which case we find ourselves in the same state of the world here, or it can go down by a factor of d, and then we find ourselves here with an underlying asset price of S times d squared. And then we suppose that we're looking at some derivative which gives you a single payoff at this point in time after two steps. And we look at this derivative and we check the small print, and the small print says, here you're going to get a payoff of PUU, and here you're going to get a payoff of PUD. So these are some number of pounds. And here you're going to get a payoff of PDD. P down, down. The payoff in the down, down state of the world. And you want to find what is the price of this derivative at time 0. Okay? So how are we going to do that? So we're going to use our imagination. We're standing here, and we're going to say, okay, I don't know how to solve this problem, but let's imagine ourselves standing in this state of the world. When I find myself, if I find myself in this state of the world, I know how to solve the problem. Because now I'm here, after one step in time, I'm going to get either to this state of the world or that state of the world. My underlying asset price is going to go up by a factor of u or down by a factor of d. And I know how to find the price of the derivative here. That's what we've just done. And then going back to the present, I imagine myself not being in this state of the world after one step in time, but in this one. And if I find myself here, I also know how to solve the problem. Because if I find myself here, I'm going to say, I live in this very simple world in which after one period of time, I'm going to find myself here or there. I know to find, if I find myself here, I know to find the price of the derivative here. But now I know what's going to be the price of the derivative if I find myself here or there. And now when I think about the future, I say, after one step in time, I'm going to have something which is worth some amount of money I can calculate, or another amount of money I can calculate. So I can now use my model for the very simple kinds of world in which one of two things happens after one step in time, and find then what is the value of this derivative here. Okay? So I can use this very simple model of the world to go my way back from the last step in time to the previous step in time to the previous step in time until I can go all the way back to the present and find the price of the derivative there. Now, if you have no clue what I'm talking about, that's okay, because I'm going to do this in a bit more detail now. So let me start telling you the details of this calculation, then we'll finish this next time. So I'm going to complicate the world a bit. So now we're going to have several steps in time. In this particular example, we're going to have 2 steps in time. So underlying asset prices are going to change twice between now and the expiration of some derivative. Each time, the underlying asset price is going to go up by a factor of u or down by a factor of d. And then I look at what can happen after 2 steps in time, so I can find myself in 3 different states of the world. And I read the small print, and I find that in the corresponding payoffs for these 3 states of the world are PUU and PUD and PDD. And then I'm going to make some assumption about interest rates. I'm going to say all interest rates are the same. They're all equal to R, and each step in time takes delta t years. And now I'm going to repeat the picture I've just drawn. And I'm going to ask myself, how do I find the price of this derivative now, at time 0? So I'm going to give names to the various nodes in this tree. So here they are. So I'm standing at present at node A, and then after one period of time, I'm going to find myself in node B or node C.